think now it's 3 o'clock, so we can get started. So Eric, if you don't mind giving an introduction for Emily.
Yep. So today it is my pleasure to introduce our speaker, Emily Matijevich. Emily is currently a PhD candidate at Vanderbilt University, and she will be defending her thesis next Tuesday. During her time at Vanderbilt, she was advised by Dr. Carl Zellick. Carl's name may be familiar to some of you, as he was one of Art Quo's trainees while he was at the University of Michigan. And he was also my advisor for my PhD. I'm also excited to inform everyone that Emily will be joining us in the HPL in February as a postdoc under Dr. Ben Onig. Emily graduated from the University of Illinois at Urbana-Champaign in 2012 with a degree in bioengineering and went directly into her PhD. During her time at the University of Illinois, she researched assistive technology and imaging techniques. This seems to have carried over to her research at Vanderbilt University, where she examined the validity of dynamic ultrasound imaging of muscle fascicles and also examined how wearable technology can be used to reduce the risk of injuries and overuse injuries. She applied this knowledge during an internship with Brooks Running Research Lab, where she explored how to provide runners with meaningful biomechanical estimates outside of the laboratory setting. Her eventual goal is to continue in this vein of research, namely to perform research in an industry setting to help people through wearable health and wellness tools, or to be in the field of sports technology. Outside of research, I would say that Emily really enjoys being outside, whether that's gardening, hiking, biking, climbing, or yogaing. One of the things that has always stuck out to me about Emily is her compassion for others as well, whether that's making homemade cards to celebrate special occasions or her willingness to help others through her research. With that, I will hand over the presentation to Emily for her talk on obstacles and opportunities for monitoring overuse injury risk with wearables.
Awesome. Thanks so much, Eric. That was a great introduction. Okay, can everyone see my screen? Great, awesome. Hi, everyone. Thanks so much for having me to present at the HPL seminar today. I'm really excited to share a little bit about myself, about my research, and also hear from you your thoughts and feedback. So Eric gave a great background, but I'm just going to share a little bit about myself as well, because it really motivates why I'm so passionate about biomechanics. So I'm originally from right outside of Chicago, Illinois. And growing up, I was really passionate about dance. And right when it was time to apply for college, I actually tore my ACL dancing. And while at the time this was very disappointing, getting to interact with my doctors, surgeon, and physical therapist really opened my eyes to the field of movement science and biomechanics and motivated me to pursue a field of study that would help me learn this. So sometimes I joke that falling in dance sort of helped me fall into this field of engineering. So after that, I did my bachelor's in bioengineering at the University of Illinois, where I started getting involved in biomechanics and biomedical research. And then from there, I moved to Nashville for the mechanical engineering PhD program at Vanderbilt. And for the past 4.5 years, I've worked with Carl Zellick in the Center for Rehabilitation Engineering and Assistive Technology. And as Eric mentioned, I'm defending my PhD next week. And Vanderbilt is also where I first met Eric. And in case he hasn't shared this with you, one of his key contributions to the lab while he was there was a very sophisticated study exploring a unique form of locomotion called prancercising. And you can see Eric here in the top left, along with some other grad students demonstrating this. Okay, so today I'm hoping to share a subset of my PhD research in which I've explored using wearables to monitor overuse injury risk. then give you a glimpse of a few other projects I've been involved in, and then tell you about some of my ongoing research interests. And before I dive into some of the details of my work, I want to share with you what I think are some key takeaways regarding obstacles and opportunities for monitoring overuse injury risk with wearables. First, I think that the use of wearables to understand overuse injury risk should be informed by the mechanism of injury, not by convenience or intuition alone. I think that wearable algorithm development benefits from both biomechanics and data science domain knowledge together. And I think creating wearables for injury risk monitoring still has many exploratory and open-ended questions for us to dig into. So why are we focused on overuse injuries? Overuse injuries are a substantial and persistent burden on our society and can result in physical pain, missed training or work, decreased productivity, healthcare costs, and psychological distress. The repeated loading our bones, muscles, and tendons experience during athletic activities or physically demanding jobs can put us at heightened risk of injury. Given that these overuse injuries are due to wear and tear on our body that accumulates over time, there's potential to prevent these injuries before they occur. And wearables offer an exciting, portable, non-invasive, and affordable tool for monitoring individuals continuously during their daily life. However, the excitement to use wearables in research, clinical, and commercial settings has in some cases outpaced the careful validation work that's an obstacle to ensuring they're being applied and interpreted properly within the context of monitoring overuse injury risk. And I think there's really an opportunity to overcome some of these obstacles and create new improved tools to monitor injury risk by combining wearables, biomechanics, and machine learning. To tackle this, I first assess what obstacles exist with current wearable tools aimed at monitoring overuse injury risk. Next, I've helped identify and create new opportunities to improve on these wearable tools. And finally, I'll share some specific ways I think these tools can be used in research, clinical, sport, and occupational communities to help reduce the risk of injury. And the two applications my PhD work has focused on is creating wearable tools for monitoring bone stress injury risk in runners, and creating wearable tools to monitor low back overexertion injuries in individuals that perform repetitive manual lifting. And first, I'm going to talk about running wearables. We were interested in monitoring injury risk in runners specifically because of the high prevalence of bone stress injuries in runners, military cadets, and other athletes. And the first thing we asked was what running wearables currently exist and what are some obstacles with how they're being interpreted and applied to understand overuse injury risk. And there are indeed numerous commercial running wearables on the market that provide feedback to the user regarding loading on their body or overuse injury risk. Many of these products use pressure sensing insoles or inertial measurement units mounted on the shoe or lower leg to measure interaction forces between the runner and the ground reaction force, or correlated metrics like peak tibial accelerations or tibial shock. However, there's strong evidence that bone overuse injuries can be modeled as a mechanical fatigue process, where the repeated loading on the bone causes an accumulation of microdamage that eventually leads to overuse injury. So if we're interested in monitoring bone damage and bone overuse injury risk, the load on the bone should be one key signal we would be interested in monitoring. And unfortunately, the ground reaction force is not the force always experienced by musculoskeletal structures inside the body. For example, the tibia bone experiences peak forces that are 6 to 14 times your body weight during running, whereas the peak ground reaction forces are typically 2 to 3 times your body weight. And it's unknown if there's some relationship between ground reaction forces and tibia force, such that ground reaction forces are a reliable surrogate for peak tibial force and associated overuse injury risk. To evaluate this, I had 10 runners run on a treadmill in a motion analysis lab, and we compared our lab-based estimate of tibial force, computed using motion capture, ground reaction forces, and a lower limb model, to a surrogate estimate of tibial force using ground reaction force metrics. And we found that ground reaction force metrics like the ground reaction force loading rate is actually a shockingly poor indicator of the tibia bone loading when running across a range of speeds and slopes. And this has severe consequences because if a wearable were to overestimate loading on the bone, you may overestimate injury risk and sideline a runner unnecessarily. If a wearable were to underestimate force on the bone, you may not notify a runner of risk before the injury occurs. And this really highlights my first takeaway that while ground reaction forces or correlated signals are convenient to collect with a single sensor, like many commercial running wearables do, they may be poor indicators of bone loading, which is a key mechanism to injury to the bone. And the lack of relationship between ground reaction force impact metrics and tibia load I saw here reinforces numerous previous experimental findings and theoretical arguments against the use of ground reaction force impact metrics as an indicator of heightened injury risk. So after we realized the limitations and obstacles of many current commercial running wearables, we sought to create a new tool for more accurately monitoring tibia bone load. We know that many current technologies rely on ground reaction force metrics like the impact peak, loading rate, or correlated signals. And we were curious if fusing data from multiple wearable sensors could help us more accurately estimate tibial loading while running. We envisioned a solution could involve some combination of inertial measurement units, or IMUs, and pressure sensing insoles, as these are the types of sensors already used in some commercial running wearables. And while I won't fully walk through the details of the two approaches we explored, one algorithm emphasized the physics of bone loading by combining both the force and motion data that could be estimated with wearables, and the other leveraged machine learning techniques. To evaluate our methods, we plotted the ground reaction force surrogate estimate, or wearable algorithm estimate, on the x-axis, and our lab measurement of peak tibial force on the y-axis. These multi-sensor algorithms we developed reduced our errors in tibial force estimation by up to 4 times. And this shows us some exciting potential for more accurately estimating tibia loading by combining data from just a few wearable sensors. And here I want to highlight my second takeaway, that while machine learning techniques do allow us to develop models that are really good at minimizing estimation error, developing and evaluating these types of algorithms doesn't happen in a vacuum. And I really think this approach is better termed biomechanics and machine learning, because the input signals we chose to collect, the discrete features we chose to extract from time series signals prior to algorithm development, and the set of running conditions we chose to collect to train and test the algorithm performance were all informed by biomechanics domain knowledge. So this shows us it's likely feasible we can create a wearable tool to monitor tibia bone loading during running. And a question we're commonly asked is, how accurate do our estimates of tibial loading and tibial force actually need to be? And this is absolutely one of those open-ended questions that I mentioned in my third takeaway. And it will likely depend on the exact application of this tool. But one way to gain insight on this topic is we considered the relationship between bone load and bone microdamage, since these overuse injuries are believed to result from an accumulation of microdamage. We use 2 established principles. First, that bone force is exponentially related to bone damage. And second, that cumulative bone damage over a workout can be estimated as the sum of damage over a series of loading cycles or running stride cycles. We then imagined a runner with a history of tibial stress fractures who wanted to monitor bone damage across multiple days of running workouts. If the runner completed multiple running workouts of differing intensity, this may be information the runner wants to capture to understand which workouts lead to more or less wear and tear on her tibia bone. We simulated these differing intensity workouts by using our lab-based estimate of tibial force and varying combinations of running stride cycles taken at different speed slope combinations. And the bone damage for each workout is shown on the y-axis, and this is shown for 20 independent running workouts on the x-axis. And if a runner were to use the ground reaction force loading rate based estimate of bone damage, they'd be misguided about how much damage their tibia bone experiences during each workout, with some workouts being largely overestimated and some being largely underestimated. Alternatively, estimating cumulative bone damage per run using the machine learning algorithm more accurately captures estimates of bone damage per run. Particularly, it captures key trends in higher versus lower damage workouts. And while it's not yet clear what level of tibial force estimation accuracy is sufficient or acceptable for different applications, our findings here highlight the importance of considering tissue damage, not only force, when developing musculoskeletal loading tools aimed at injury prevention. And there's still a lot of validation and translational work that is necessary to get these types of algorithm approaches deployed on consumer-grade wearables. But once we have a practical and accurate tool for improved monitoring of tibia bone loading in runners, what could we do with it? And I think an important thing to remember is that once we have a reliable estimate of a given single biosignal, it can really open up numerous opportunities for gaining insights. For example, while heart rate is just a single biosignal, it allows us to draw insights ranging from our exercise exertion to our sleep quality. For a tibia load monitoring tool, I could imagine it could be used for daily risk monitoring in recreational to elite athletes, warning users when their leg bones have accumulated a lot of damage, and it may be worthwhile to take rest days to allow the bones to recover. I think it could potentially be used in a clinical or rehabilitation setting to guide and inform return to play progress. I think it could be used in a research setting to evaluate how different interventions like footwear or performance enhancing exoskeletons change the loading on the bones inside of our body. And I think it could also be used as a training tool to help athletes understand if there are certain running strategies that may minimize the loading on the bone with each stride. So in summary, we know that many commercial running wearables rely on ground reaction force metrics or correlated signals, and these may be unreliable indicators of bone loading. And multi-sensor algorithms seem like a promising opportunity to improve on bone load monitoring. And I think there are many sport, clinical, and research applications to reduce injury risk if this type of tool was widely available. Okay, now I'm gonna transition and walk through a similar process for monitoring low back loading. And we were motivated to explore tools to monitor low back loading because up to 85% of adults experience low back pain within their lifetime. And 1 in 4 work-related injuries is related to the low back. So first we evaluated what tools already exist to monitor low back loading and what are some obstacles with how they are used and applied to understand overexertion injuries during lifting. There are current commercial wearables on the market that give feedback on injury risk in occupational settings. Most of these devices, like the ones shown here, use a trunk, chest, or waist-mounted IMU and focus on identifying high-risk postures and movements, but they don't necessarily provide insight into low back loading. And similar to bone stress injuries, there's strong evidence that low back pain is also a fatigue failure process. Lumbar moment over a work shift has been shown to be a key metric that's significantly higher in workers that experience low back pain. And a risk assessment tool that estimated lumbar moment over repeated lifts has been validated against 2 occupational epidemiological injury databases, and has been shown to explain up to 95% of the deviance in low back disorders. And in addition to this evidence that monitoring low back loading is key to understanding these low back disorders, I also want to share a few conceptual examples why trunk orientation or upper body orientation alone doesn't necessarily tell us the full story of the loading or low back experiences. So I first want you to envision that you're leaning forward holding a 10-pound mass, which is about the weight of a watermelon, versus you're leaning forward holding a 50-pound mass, which is typically the maximum object weight that individuals are allowed to lift on the job at work. And if our massless stick figure was holding each of these masses with the same trunk lean, the second would result in about 5 times greater lumbar moment. As another example, if you're holding an object close to your body versus you're holding it far in front of you, Despite equivalent trunk postures, the second example would result in about 4 times greater lumbar moment. And both of these examples highlight that similar trunk postures can result in very different magnitudes of lumbar moment. And we likely want to capture these different magnitudes of lumbar moments with our wearable monitoring tool that's aimed at identifying injury risk. And again, emphasizing one of my takeaways, while a single sensor solution is convenient for workplace implementation, these differences in lumbar moment that are primary to the injury mechanism are likely completely missed by current technologies used in an occupational setting that only measure trunk posture or motion. So because of this potential limitation and obstacles with these current technologies, we sought to envision a new tool for lumbar moment monitoring. And we were curious if, similar to our tibia bone project, could fusing data from multiple sensors more accurately estimate lumbar moment. And we focused on a potential solution that was accurate over a broad range of manual lifting tasks, so it would apply well to the complex motions performed in a workplace environment. And we also wanted this tool to be practical for workplace implementation by only requiring a small number of wearable sensors. To explore this, 10 participants came to our motion analysis lab to perform a broad range of more than 400 different manual lifting tasks. These tasks, like the ones you see here, cover various leaning, twisting, and lateral bending postures while moving boxes weighing 10 to 50 pounds. And these were representative of tasks performed by manual material handlers. During this data collection, I synchronously collected lab-based and wearable sensor measurements. We used our lab-based measurements, motion capture and ground reaction forces, and inverse dynamics to estimate our target low back loading metric, lumbar moment. And next, we used our wearable sensor signals to explore different reduced sets of sensor combinations. For example, current wearables seem to use a single sensor combination, to then use these signals to develop algorithms that would estimate lumbar moment. And we characterized the performance of over 60 different wearable sensor algorithms using 1 to 6 sensor locations. And for each algorithm, we computed accuracy with higher values indicating a strong correlation between lab-based lumbar moment and our wearable algorithm estimate of lumbar moment. And here, each dot represents the average accuracy of each algorithm using different combinations of wearable sensor signals. And as expected, maximum algorithm accuracy increased as the number of sensor locations increased. And also, none of our single sensor algorithms resulted in a particularly high average accuracy. And with all these algorithms, we found the most promising results using gradient boosted decision trees, and accuracies reported here are the average accuracies from the k-fold validation by participant. And we further inspected 2 sensor combinations, the highest accuracy single sensor algorithm and the highest accuracy algorithm using 2 sensor locations. And we compared these to our more distributed sensor algorithm shown on the right. We found that using 2 sensors, which is the option shown in the middle, provided a jump in accuracy compared to our single sensor algorithm, which is most similar to current commercial technologies that only measure trunk orientation. And this 2 sensor algorithm sacrificed minimal accuracy compared to other options on the right that used more sensor locations. And while we did anticipate that a trunk IMU alone would not capture all changes in lumbar magnitude, particularly with objects of varying mass, we inspected time series results for these 3 examples to gain more intuition. And for these results, I'm going to show lumbar moment on the y-axis for 3 example pick and place tasks, which is where the participant is holding and moving a box on a shelf. And comparing our lab-based estimate of lumbar moment with larger values here being higher magnitude extension moments to our wearable algorithm using a trunk IMU only, we see that the algorithm misses some key trends in low back loading, particularly at the larger magnitude moments. Alternatively, using additional sensors is able to better capture these elevated low back loads. While the trunk IMU alone may capture when the person leans forward and elevates their low back loading, it does not capture the increasing lumbar moment when the individual has a heavy object in their hands, such as here where they were holding and moving a 10-kilogram box during these areas in gray. And this is another time I want to highlight my takeaway of the benefits of using both biomechanics and data science skills. For example, biomechanics knowledge that the lumbar moment changes with when varying object weights motivated the inspection of these time series results, particularly at the higher magnitude lumbar moments, which are of highest interest because they're most damaging to musculoskeletal tissues and contribute most to injury risk. And also we gain confidence in this machine learning algorithm because the fact that our model ranked this two sensor combination as most promising matches our biomechanics intuition, given that lumbar moment is influenced by the mass of the object which is being lifted, which can be partially captured by pressure insoles, and by how much the person is leaning forward, which can be captured by the trunk IMU. And I think biomechanics and data science together here help us critically evaluate both the success and limitations of these different wearable algorithm options. And again, if this tool requiring a small number of sensors to accurately monitor low backloading was widely available, how might we use it to reduce the risk of injury? And similar to the Tibia project, I think there are likely many exciting ways this tool could be used and applied. I think about construction workers that are required to wear a safety helmet to protect them on the job. And maybe one day workers that perform repetitive manual lifting will be required to wear a lumbar load monitor to warn employees when they have done too many strenuous jobs in a row. I think this type of tool could supplement current ergonomic assessments of workplace environments that typically require a trained professional to monitor and manually information about the tasks an employee is doing. And this is currently really time consuming and expensive and not feasible to apply to widespread workplaces. And I think this type of tool could also be used as a control signal, such as to provide smart actuation to assistive devices. This could allow devices to provide more assistance when the loads on the low back are high and less when it isn't necessary. So we know that many occupational wearables emphasize posture and motion, which can misguide our understanding of loading on the low back. And it seems that multi-sensor algorithms, such as one using a trunk IMU and pressure insoles, could be a promising way to improve by still requiring a small number of sensors, which is practical, but offering more accurate estimates of low back loading. And I think there are many occupational and clinical and research applications if this tool was widely available. Okay, and I want to circle back to my 3 takeaways again. So first, I think the use of wearables to monitor overuse injury risk should be informed by the mechanism of injury on a specific musculoskeletal tissue, not solely by the convenience of data we can collect with current wearables. Second, I think this is an exciting cross-disciplinary field, and I think wearable algorithm development for monitoring injury risk is not purely a black box process, but rather benefits from combined insights from both biomechanics and data science and machine learning. And finally, even though there is sophisticated wearable sensor hardware, I think there are still numerous exploratory and open-ended questions regarding developing algorithms and analytics that give us good information about injury risk. And there are still many questions surrounding how we apply and use these types of tools. Okay, and now I'm gonna walk through just a few additional projects that I didn't share in detail. As Eric mentioned, my first PhD project was using ultrasound to evaluate tendon dynamics in vivo. And I think ultrasound and other imaging modalities are really exciting tools to peer beneath the skin and evaluate the function of muscles and tendons during movement. I also have an interest in sports tech, and I received a fellowship through the Women in Sports Tech organization that allowed me to do an internship with Brooks Run Research Lab, evaluating how we can use wearables to see how footwear influences running mechanics outside the lab. I'm very passionate about science communication, and I've enjoyed sharing and interacting with the community through Twitter, some data interaction tools I've created, and also through a few blog posts. And finally, I really love science outreach, and I've enjoyed helping lead our lab's National Biomechanics Day efforts each year. And I've also been involved in a variety of youth education programs at Vanderbilt. And moving forward, what are some of my ongoing research interests? One is using wearables to evaluate interventions like assistive technology in the wild, whether that be in home, sport, occupational, or clinical settings. So we can better understand the device performance during functional and realistic tasks. Also, while much of my PhD research has focused on load monitoring wearable tools, there are certainly many other risk factors that contribute to overuse injury risk. And I'm curious how sophisticated or personalized injury risk monitoring tools need to be to reasonably guide injury prevention protocols. And finally, I was very fortunate to try on and wear many different assistive technology prototypes during my PhD studies, whether that be exosuits or different footwear prototypes. And I'd really love to learn more about how our perception of the assistance and benefit from a device aligns with quantitative biomechanical outcomes, and how we can use these outcomes together to create products that satisfy a user's intent and preference. Outside the lab, again, as Eric mentioned, I love being outdoors. I love hiking, cycling, climbing, gardening, practicing yoga. I also really love to travel. This is a photo from a few years ago where I traveled with some other PhD students to Costa Rica. And I also really love doing art projects. And my favorite is sketching and painting with watercolors and inks. And yeah, I'm defending my PhD next month. I'm currently in Nashville, and then I plan to make my way up to Chicago to visit some family. And then I'm very excited to be up in Calgary by February of next year. And yeah, thank you so much for having me. I've learned so much from Carl and the rest of my lab during my PhD studies. So a huge thanks to them. And also a huge thanks to a lot of people that are likely in the audience right now who have either been a mentor to me or engaged in scientific discussions with me, or who have just published really rigorous research that has helped shape and inspire some of my graduate studies. So thank you, and I'd love to hear any questions or comments.
Thank you very much, Emily, for sharing your work with us. Before we get the discussion started, I would like to gently encourage you to turn on your web camera during the discussion period if you feel comfortable with it. Thank you very much. If you have any questions to our speaker, Emily, please use the raise hand button that can be found if you click the participants icon at the bottom center of your screen, and you will see the blue icon raise hand button at the bottom on the right-hand side. Does anybody have any questions? Yes, Reed, please go ahead.
Hi, Emily. That was a really nice presentation. Thanks very much. I do some wearable sensor research around here, and I have a few questions, but I guess I want to start with your takeaway. So what exactly do you mean by convenient? Give me an example of a convenient data collection that we should avoid. And how exactly, I think you've given some examples of more directed placement of IMUs, but I just want to kind of tear apart this, I just want to discuss more about this convenience factor that you've brought up.
Yeah, absolutely. And I'd love to hear your opinion on this as well. I admire a lot of your work. I think for these two applications, I think I was often using the term convenient to refer to single sensor solutions. I think it is easy for workplace implementation and sport implementation to place a single sensor on a user. But I think the value you add by just increasing that to maybe 2 sensor locations is really worthwhile if you're getting better load monitoring tools. But I think, I think I was using the word convenience in terms of maybe the number of sensor locations or how distributed sensors are in the body. But then I think there certainly are other metrics or signals we would want to monitor in which a single sensor or the raw signal from a sensor may be sufficient. Yeah, I'd love if you had any other thoughts on that.
Well, yeah, I think you have a nice example there where you show that the algorithm accuracy or R-squared value is the same for 6 sensors as it is for 2. And then, we published a paper a while ago showing that the predictive algorithm or the predictive accuracy of determining rehab outcome was about 76% with just 1 sensor. That jumped to about 83%, and then we didn't gain anything else by adding in 4 or 5 more sensors and all of that. But yeah, I think that's a nice explanation of the word convenient. I now understand that a little bit better. Thanks.
Okay, Olivia, I see you have a question to Emily.
Yes, hi Emily. So more of a hypothetical question. So I know you've predicted tibial bone force, but if we're talking about stress fracture prediction, if you want to compare between people, you're going to have some sort of measure of bone quality. So do you think if you had some measures of bone geometry and material properties, if those could be used as inputs for your algorithms, and that you might be able to predict tibial stress or strain?
Yeah, I think that's such a great point. The load monitoring is one small piece of the puzzle to, I think, understanding the overall injury risk. And I think that's a really nice example of a way to maybe personalize the monitoring and personalize the tool for a person based on those types of intrinsic factors. So yeah, I think that's a great suggestion and a great point.
Okay, Andy, do you have any questions to Emily?
Yeah, thanks for your great talk, Emily. In terms of the machine learning algorithms that you're talking about, 2 of the main critiques of machine learning in general tends to be either to do with the generalizability of an algorithm and or kind of related the interpretability of an algorithm. So I was just wondering, with your, you presented some k-fold cross-validation results there. I was wondering if you had any insights on how well your algorithms generalize, say, between person and person or between task to task, or even as it pertains to practical application in the field, how much this may change if you were to, say, move a sensor in terms of your sensor placements for maybe a day-to-day piece there.
Yeah, I think those are all great points and very relevant concerns that we should have when we think about translating these into the real world. To address the first question about generalizability, yes, we did train the models by withholding 1 participant. So then when we compare our participant-specific k-fold validation results, and when we don't see huge differences in accuracy between each of those participants, I think that gives us a little bit of confidence in the generalizability. But again, each of both the running study and the low back lifting study had 10 participants each. So we acknowledge that that is a relatively small sample size. And I think, I'm not sure if this was included in the question you asked, but another question we often receive is, if there is different black box models being used in these machine learning algorithms, how do we know that they generalize to tasks we did not collect in the lab or we didn't evaluate their accuracy? And I think 2 promising things related to that is, 1, there is potential to kind of do a hybrid approach where we partially use biomechanics and physics to estimate musculoskeletal loading part of the way, and then just leverage some machine learning techniques to help us tune the accuracy. So physics is always true, so we have some confidence that way. But I think another interesting reason why we may have some confidence in these algorithms is the types of signals the machine learning algorithms end up ranking as most important typically do match our biomechanics intuition on which signals do change with differing bone loading. So that gives us an extra set of confidence, I think, about the generalizability of these algorithms. And I think I already forgot the second part of your question.
Oh, it's just around, what's the word? I've even forgot the second part, so it's all good.
Yeah, and I'm also just curious if anybody has any other gut checks or sanity checks or things that they consider when they think about deploying these types of algorithms that may leverage machine learning techniques.
Okay, Brent, do you have any questions?
Yeah, hi Emily, great talk. You have a physics-based laboratory, you have a physics-based model that you use to, with the laboratory-based measures that you use to calculate this tibial bone load metric. And then you have the physics-based model that you use with the wearable sensors. And it didn't do as well at predicting tibial bone load as the machine learning approach. And I'm just wondering what is captured in what is not being captured rather in the physics-based wearables model that you're able to measure in the laboratory.
Yeah, I think two key parts of the equation that we don't get to measure with current wearable sensors and we can't quite account for is one, current pressure sensing insoles typically measure a one-dimensional ground reaction force, whereas in the lab we measure three-dimensional ground reaction forces, and that entire ground reaction force vector can contribute to loading on the bone. And then two, when we account for muscle loading, that's related to that ankle moment. Because in the lab, we're able to do calibrations and inverse dynamics that really accurately estimate that lumbar or the ankle moment. When we only have a center of pressure or an insole that has force and center of pressure, we kind of have to make some guesses about the position of the ankle relative to the insole center of pressure.
Yeah, okay, that makes sense. And if you had to guess which one had a bigger influence on the error, whether it was the fact that you can only measure something that's normal to the foot versus you have to make a guess on what the moment arm is, what would you guess that it is?
I think given that muscle forces contribute most to tibia bone loading, and given that guess about center of pressure relative to the ankle joint in some ways dictates our wearable estimate of muscle loading, I would think that might contribute more, but we never evaluated that. And these are other questions that are really influenced by when you decide to deploy this on an actual consumer grade wearable, right? Because the actual wearable you choose to use is going to have different spatial resolution of sensors, which then can start affecting your center of pressure quality estimates or resolution. And that's a concern, right? If that muscle contraction component is of high interest, and then we start having to make more guesses about that. So do you have a guess maybe which would contribute more?
I'm guessing, I mean, of course, the orientation of the vector is gonna contribute to the moment arm about the ankle as well. But my hunch is that because the peak value is probably coming around mid stance, that it's probably gonna be more so the shear components of the ground reaction force are not going to be that prevalent. And so it's probably more so, like you say, this estimating where the center of pressure is relative to the ankle joint. That's my hunch. Yeah. Cool, thanks.
Okay, Reed, please go ahead.
Okay, so you collected all the data in a laboratory on a treadmill. So what's going to happen to these algorithms, do you think? Let's just be hypothetical here. What happens when you go out into the real world? What do you think is going to happen to your algorithm?
Yeah, that's a great question. And it's great that we've had some new members join the lab, and they're actually trying to start digging into that and understand the reliability and repeatability of these types of algorithms across participants, across days, and when we go outside the lab. I think that, there are some ways to maybe do some gut checks and sanity checks once we start collecting trials outside the lab. We have some intuition about how bone loading may increase with increasing speed or increasing slopes. But I think there's going to be hiccups, right, with these wearable sensor algorithms, especially, you know, if you're using a pressure insole, as soon as you start maybe, I don't know, being on some gravel or some rocks, does that make your shoes start sliding around more and your insole starts shifting? So I think one thing we might have to start exploring is how we can do any sort of like frequent calibrations to the algorithm. You know, is there some body position or movement condition that a runner may do periodically where we can kind of reset or recalibrate our algorithm in case there are things like sensors moving over time.
Yeah, you could apply like a Kalman filter to it, or develop like a dead reckoning system some way to account for that, because now you're out in the real world and people sweat and it's hot out and it's much longer in duration. And our fun experience was just realizing that we were collecting data outside, and the data wasn't making any sense. And then we started realizing that the runners were stepping off the curb and onto the road and back on. They're dodging other pedestrians. And we have data of people running from dogs, and so you just never know what that's gonna. But my question still remains: what do you think is going to happen to your algorithm? Do you think it's going to hold up, or are there other factors? Do you need to increase the number of sensors then to account for all these other new real world, or in the wild, I think was your term, factors?
Yeah, I think I don't know the answer for sure. I think if we either use some of the physics-based approach or some fusion approach, that will still have some confidence in the form of these algorithms, even when we do go outside the lab. But I do agree that there might be numerous needs related to tuning the algorithm and calibrating the algorithm. But I don't initially suspect that more sensors and more sensor locations may be necessary, but I couldn't say for sure.
Fair enough.
Okay, I see Valentina, you have a question for Emily?
Yeah, thank you. Thank you, Emily, for the wonderful presentation. I have a curiosity about the user perception. Of course, we are all excited about getting better, more accurate results, but sometimes we're puzzled by the users not actually perceiving the quality of our data. So I was wondering what's your thoughts about it and your strategies, since you mentioned you're interested in this area as well.
Yeah, I think one interesting study in our lab that I was able to be a participant in was testing a low back exosuit that would offload some of the low back muscles when you did lifting tasks. And they were trying to understand if there was an optimal stiffness of the springs used in the exoskeleton that would provide the most assistance to the user. And while they also measured how much assistance the exosuit was providing, they also asked the participants after each task, how much did you feel like the exosuit was helping you? And I think one interesting thing they incorporated into that experimental protocol was they made sure that they were going to include exosuit springs that provided so much awesome assistance, but they knew it would not be comfortable to the user. So kind of pushing them past a comfort limit, and then also going the other way on the spectrum, using a spring that provides so little assistance, but maybe it feels nice because you're also not getting any of the bulky resistance from the spring. So I think one interesting idea is maybe trying to really push users to their bounds of comfort and preference. But yes, perception and perceived benefit and perceived assistance is still something I'd love to learn more about.
Okay, I see Ziska, you have a question.
Yes, thank you. That was very interesting. I'd be really interested in what you would have in mind, how you will use this information of the loading to inform the users. Like, are you assuming that too much load is always bad, or how would you account for the capacity of the individual, and what will, like, how can they actually use the data?
Yeah, that's a great question, and probably some things that people in this group would be better to develop out than I would be. Again, I think creating accurate tools to monitor loading is certainly just one piece of the puzzle. And using this load information to then account for the individual's damage accumulation and remodeling and their specific tissue capacities are certainly all factors that need to come together to provide actionable warnings to the user. But I really think that by developing musculoskeletal load monitoring tools, you at least provide a signal that helps you build out some of those predictive models, I would hope.
Okay, thank you. And
Thanks.
sorry, can I just, so how far do you think we are from going from the data that you have now to actually being able to, I don't know, get the information on an app and telling people, okay, you're doing too much, you should slow down? How far you think, just like, what do you think?
Yeah, unfortunately, I think it's probably still years, maybe. I think one big first stage is, like Dr. Ferber mentioned, a lot of this has been done in a lab, and getting this translated into commercial wearable sensors and validating that is a step in and of itself. And then second, how do we decide those thresholds where we give individuals warnings? And I think a key thing that needs to happen for that is some sort of running prospective study where we monitor a group while they're wearing this sufficiently accurate tibial load monitoring tool, and we can kind of line up injury incidents with tibial loading information over weeks and months. So I think those two steps together, I would think, would take years.
Thank you.
Okay, I see Michael, you have a question.
Thanks for the talk, Emily. That was really nice. I guess my first question is, do you actually think we'll ever be able to prevent injuries using a wearable device? And then the second one is kind of building on that, is saying, is the accuracy of the sensor that's needed dependent on the scenario? So maybe an injury prevention setting requires really high accuracy, whereas maybe a rehabilitative setting requires slightly less accuracy. So is maybe one in your mind more feasible kind of avenue to achieve than the other?
Yeah, that's a great question. To your first one, I think there's potential to use wearables to reduce the risk of injury. And I think even I probably sometimes for shorthand use the phrase prevent injury, but I think a lot of these tools should be thought about in the context of reducing injury risk. And we'll never have, at least I can't envision perfect injury prevention tools. And then with your second question, I absolutely agree that the level of desired accuracy could change based on the desired application. So some of these single sensor solutions that I kind of, criticize because they're convenient, but that level of accuracy certainly may be acceptable for certain applications. And I think for applications that want really high accuracy, there's even opportunities maybe I didn't talk about, like if you have a really elite athlete, what if you could have them come run in the lab for a day, but you can really tune the algorithm to that specific person. So then when they do go out in the real world, that algorithm has been optimized to have potentially even higher accuracy for that individual if time and money was, worth it for an application. So I definitely agree with your second point.
Yeah, I think that's quite interesting what you brought up about kind of if you have one person and unlimited resources, you're probably likely to get somewhere much faster than if you're trying to generalize something across.
Yeah.
Cool. And maybe it's interesting to see if these elite sports will be the first people to get there because simply they have the resources to do it.
Right.
I don't know.
Right. We should have gone to the NBA bubble where they spent all the money on all the sports things, and we could have been monitoring their tibias while they were there.
Thank you.
Benno, I saw you have a question for Emily.
Yes, thank you. Now, all the variables that we have are basically limited to accelerations and positional data and stuff like that. There's no information about muscle activity. Do you think if you would have that information in addition to what you have now, that you would be better off, and how so?
I think absolutely. I think our most promising solutions for monitoring tibia bone loading and low back loading involved a combination of motion and force data. So motion data from IMUs and some information about force from pressure insoles. And while force under the feet or under the shoes isn't directly equivalent to individual muscle forces, I agree if there wasn't the challenges with using EMG day to day and across multiple days, similar to how force information under the feet can really improve our musculoskeletal monitoring tools. I do think that EMG that gave reliable estimates of changes in muscle force magnitude could also be really beneficial for sure.
But what specifically would you look for?
So like for the tibia bone loading, we estimated muscle forces by using the pressure insole and IMU to estimate ankle moment. But alternatively, you could put an EMG sensor on your calf muscle and track changes in gastroc and Achilles tendon loading that is compressing the tibia bone. And the low back is like a mess of muscles. But again, in a perfect world, if we could monitor all those low back muscle forces that were compressing discs or muscles that were at risk of tears, I think that could be beneficial for overuse and overexertion injury monitoring.
So let's assume you measure force and EMG. And what would you look for? Would you look for the amplitude, look for the frequency content? What would you look for?
Yeah, I think in some of these applications, when we're considering the loading on structures, maybe that's peak compression force on the tibia, for example, or peak bending moment on the tibia. From my background in EMG, I would think changes in EMG amplitude may give you some information about relative changes in EMG or in muscle compressive force. But I certainly do not have the sophisticated background in some of these other EMG analysis techniques yet that might have applications. Do you have thoughts about particular scenarios, how to use other EMG techniques for injury monitoring?
Okay, I see Walter, you have a question.
Thanks, Songwan, and thanks, Emily, for I really enjoyed the pictorial depictions of some of the variables that you measured. I think that was really cute and very useful, actually, to see what you meant by what you said. I got thrown out a couple of times on the internet here, and just when I came back, you.
Okay, I think we lost him, right?
Yeah, he should pay his bills.
200 kilometers per week for 10 years and never had a stress fracture.
Sorry, Walter. We actually lost for you for a couple of seconds. So could you just go over once more?
Yeah, sorry about that. I seem to have an unstable connection. I've been thrown out several times. So if I get thrown out, just forget about me. But I've known runners that ran for 10 years, 200 kilometers per week, and others that ran less than 40 kilometers per week. And the one with 40 kilometers per week had multiple stress fractures, and the one with 200 kilometers did not. So the question is loading really important for stress fractures, or is the biological material that you have available more important potentially?
Yeah, great question and great point. And I think it's likely a combination of both. Two runners could run the same distance. They could be on the same cross-country team and have the same training, but one might get a stress fracture and one may not. And I think that's potentially because you can run the same distance, but you're choosing to adopt certain running techniques that change the peak loading on your bone, which influences that damage accumulation. But I certainly agree with the other point and comments from Olivia and others that there are certainly runner-specific parameters and tissue-specific capacities that are going to influence that absolute injury risk for sure.
We have some fabulous people in Calgary that do micro CT for lower limbs, and I think I'm waiting for that study for probably 30 years now, that somebody tries to get a handle on the biology of the tibia, for example, with micro CT, and then does exactly what you have done, but then have a more adapted algorithm that takes care of the idea that people have different bones. But you were talking about the loading on the tibia, and you know, when on animals, we put strain gauges on a bone, like the tibia in a cat or in a rabbit, then we get very different measurements depending on where we do that. So when you say tibia load, what do you actually mean by that? Where do you measure that? And yeah, exactly, where do you measure that?
Yeah, that's a great question. You know, we did not make any FEA models that included that three-dimensional shape of the tibia, and we measured the peak compressive force on the tibia bone, you know, along the long axis of the tibia, but we did not measure or try to approximate any localized stresses or strains, which I think, similar to your previous comment, is another opportunity to use runner-specific morphology, maybe to try to get more localized estimates of stress and strain and see how those change over time, maybe.
The other thing that I thought was really neat, you know, in your running study, you have tibial load and tibial stress fractures, but in your low back study, you have low back injury, low back pain. What do you think gets injured? What do you think produces the pain when I'm lifting too much and I have an injury? What is it? What are you looking for? What stress, like, yeah, which tissue do you look at that gets stressed?
Yeah, I think there's so many different low back disorders that could result in low back pain. Some that were included in these epidemiological databases include vertebrae fractures, partially herniated discs, and muscle strains. And I think each of those tissues has a slightly different loading pattern and loading regime. But given the strong previous evidence that changes in lumbar moment, which influences loading on all these different low back structures, kind of strongly explain the incidence of low back pain, I think gives us good motivation for using lumbar moment to try to track this injury risk. But it certainly doesn't get us to the level of what's the specific loading on my L5, S1 vertebrae. Yeah.
And when you measured lumbar moments and when you explained it, you know, you had the nice two-dimensional pictorial depiction. Do you actually calculate the 2D lumbar moment, or do you calculate a 3D lumbar moment? Because some people think that twisting is very bad in combination with bending.
Yeah, that's a great question. And we did measure the triaxial lumbar moment, and we focused on extension moment because it is the largest magnitude, but we actually repeated all of our algorithm workflows for the lateral bending moment and found that we could achieve similar accuracy to estimate lumbar moment. And our twist moment magnitudes were small, but I definitely think an injury prevention tool should monitor twist angle, because I think if you have estimates of extension and or lateral bending lumbar moment, and then also information about the upper body twist posture, I think that together maybe gets to your point that there's some of the tissues are at heightened risk when you're in a twisted posture.
Yeah. When I watched the video of the lifting movements that you showed, that you did experimentally, it seemed to me that the people did not really move their legs, their feet very much. Were they required to stand at a place? Because some of the movements seemed quite awkward, and I would have made a little sidestep to, you know, accommodate it better.
Yeah, that's a good question. To estimate lumbar moment with inverse dynamics, we needed both of their feet on a force plate. So we told that they were able to shift or pivot or hover a foot off the force plate, but we just asked them not to step off the force plate area. So it absolutely is somewhat constrained. They're in a lab environment, and they did shift and move their feet some, but it certainly could have been not perfectly representative of that more dynamic shifting and stepping that a worker in a workplace environment may do.
Great, thanks a lot.
Thank you.
Brent, please go ahead.
Hi, Emily. So I study mechanical fatigue and mostly bone tissue tolerance. I'm a little bit upset that Walter thinks that somebody needs to start doing that work, because I thought we were doing that work. Anyways, I go around and I give these talks.
Sorry.
I talk about mechanical fatigue and damage accumulation and stress fracture risk. And people always say, well, what about repair and adaptation? I hear a lot of people talk about low back injuries as well. And everybody knows that those are overuse injuries. And I don't ever hear anybody say, what about repair and adaptation? So why, when we talk about running injuries, when we talk about tendinopathies and stress fractures, do people say, what about repair and adaptation? But when we talk about more ergonomic things, carpal tunnel, low back pain, sure there's a number of others, people are sort of less inclined to bring up those issues. Do you have any thoughts about that?
Yeah, that's a great point, and actually something I haven't thought about that much. And I really agree that there doesn't seem to be much research or documentation about the timeline and thresholds for any sort of remodeling or adaptation that happens to, for example, the low back structures. I guess my only reaction is maybe just there hasn't been enough interest and resources to do it. I don't, sports overuse injuries are sometimes, yeah, I don't really know why, actually. That's a good question.
I don't know why either. I don't know why either, but I just, it's something that I thought about, and I just didn't know if you had encountered that issue before. Thanks.
Yeah, and especially some of those tissues like the discs between lumbar vertebrae. I know very little about how those structures kind of accumulate damage and then recover when rested and things like that. So that's really interesting.
Okay, would there be any last question to Emily?
Songwan, maybe not a question, but just to reiterate what Brent was saying, I think that's another topic that I think is completely unexplored, is not only the load accumulation, but the following recovery, which I think would also again depend on some of the biological parameters. And I think it would be fabulous for somebody to just give that an initial shot and try to make it happen. I think there's a whole open area of research in looking at the recovery of tissues that undergo stress failures in any kind of ergonomic or sports environment. And people talk about running hard one day and easier another day, so that you get a little bit of break and that you might recover. But what that recovery means, what it implies on the on the overall tissue level or on the molecular level, I don't think anybody has a good handle, and I think it would be fabulous for somebody to do that. And I think Brent is ready and you're coming, so that's great.
Okay, I see Stefan, you have a last question to Emily.
Yeah, thanks very much, Emily. I really enjoyed your talk. I just had one quick question, more from a kind of load monitoring perspective. So when you think about like aggregating the information and trying to feed back to coaches or athletes, how long do you need to aggregate that data over before kind of making a decision? So is it, is it a weekly thing? Is it a monthly thing? Is it a lifetime exposure thing? How are you aggregating that data? And then, if you have an app, and I think you suggested it, like providing feedback to the athlete to say you might need to ease off a little bit here. How do you know how long they need to ease off for, and how long that kind of suggestion is going to be in place for?
Yeah, those are all really great questions. And I think similar to maybe some previous questions, are so application dependent. What is the exact use case of this load monitoring tool? And also, I don't know the answer to that. I think there is applications for more short-term monitoring, giving some daily summary of how much loading and damage your body has experienced. But I think there's also much broader opportunities, such as workplace environments that are really trying to manage their worker compensation costs, and they want to, on a large time scale, minimize the number of employees that are getting injured on the job. And I think, if you have an employee that works at Amazon for years, there's opportunities to maybe kind of keep a profile about that employee and understand what sort of load magnitudes or work shifts have they done where they have been okay and they haven't gotten injured, and then what sort of jobs and loading and cumulative damage profiles did maybe cause them to get injured. So I think all those timescales you mentioned could be really interesting, and I don't know if I have a single answer or what level of how long we have to wait to aggregate different volumes of data.
Yeah, I guess, and I suppose, do you think it's a case of looking out for prolonged exposure to high loads, or do you think it's a case of individual spikes that you see all of a sudden one day they're doing way more than other days, or whatever the case may be? What do you think? Do you think there's anything there yet to know whether it's which scenario it is, and when you need to maybe flag with either a worker or an athlete when they need to ease off a little bit?
Yeah, and I think it could be a combination of both. So, keeping track of damage across days could be really important, because you may have a moderate intensity Amazon warehouse shift, but if you do that 7 days in a row, I don't know for sure, but that could, be injurious. Whereas if I just have one really intense, really long shift, that could also be reason for warning. So I agree that it probably requires kind of a bigger picture look at, between day load monitoring and cumulative damage, and how rest and recovery kind of changes our biofeedback and recommendations to athletes or workers.
Okay, Matt, if you have any questions, please go ahead. Matt Jordan. Yes.
Sorry about that. Yeah, no, I was saying it was a really nice talk, and I'm sorry I missed the first 15 minutes of it, but I really enjoyed the last bit. But just kind of building off Stephen's question, what have you seen with regard to, yeah, exactly that, the idea of disuse? And I guess where do you see this technology possibly fitting outside of the workplace and into the real world, so to speak, where you're literally monitoring the individual 24/7, 365? Do you think that's a feasible prospect, or do you think this will be limited just to the workplace?
Yeah, that's a great question. And I think there's potential for both based on what the form factor of this device ends up looking like. If years or decades from now, we all have sensors that are seamlessly integrated into our clothing and shoes, that could be really easy to transition to monitoring you at work, to your social life, to at home, and you really can get that all day monitoring. But if the tool does look like something you kind of take some time to don and doff, maybe that is something you only wear while in the workplace environment. And I think if it is only for workplace monitoring, I think two options are, we kind of accept that we're missing out some of the damage your low back is experiencing when you're at home lifting up your kids or lifting groceries. Of course, that's going to add some cumulative damage to your low back. Or we get good at creating user interfaces that maybe have the employees input some summary about their home or social life when they're not, in the workplace environment. Is there any way we can make some really rough estimates of what's happening to their low back when they're outside of the workplace to try to account for that missing information?
Yeah, and I just really thought, that idea too with, the tibial stress fracture. I mean, I'm not sure if you've heard of the new term for what we used to call sort of eating disorders, but it's called relative energy deficiency in sport, RED-S. But, it's just this recognition of all those confounders, right? Nutrition and unloading recovery and just what's going on when you're not just doing your sport, where, a lot of times those are big contributors to some of the stuff that you're looking at. So anyways, great. Thank you very much. That was really enjoyed it. Appreciate it.
On that note, I would like to thank Emily again for sharing her work with us and the interesting talk. For the next week's seminar, which will be the last seminar in this fall term, we will be hearing from Michael Bagley, and the title of his talk is Internal Tibial Moments During Graded Running. Thank you for all for just coming today, and I'll see you all next week.